Hi, let's take a look at the formal hypothesis testing 7-step procedure which we'll use throughout this chapter. The first step is to identify the parameter of interest for the test that you're conducting. For example, it may be the mean, it may be the variance, it may be the population proportion, and other parameters that you're focusing your hypothesis on. The second step is to state your null hypothesis H naught. The third step is to find or state your alternative hypothesis H1 or your research hypothesis. And the fourth step is to identify a test statistic, just like we did earlier in the confidence interval chapter, where we decided whether we had to conduct a z-test, a t-test, a chi-square test, or use the population proportion p for conducting any of these tests. Even though for population proportion we really use a z, but so we got to identify the appropriate test statistic. The fifth step is to develop your rejection criteria. So we clearly state under what conditions is your null hypothesis rejected in favor of your alternative hypothesis. Step 6 involves the computation of the value of the test statistic, and step 7 is when you really decide whether you want to reject H naught and report that result. So these 7 steps are many times really clubbed into 1 or 2 steps, but it always helps to write these steps out clearly. That way there is a specified order in which these things are conducted. And so what we'll do is we'll take a look at some examples. Let's read an example together as a practical application. So an example of an automotive application. A bearing used in an automotive application is supposed to have a nominal inside diameter of 1.5 inches. A random sample of 25 bearings is selected, and the average inside diameter of these bearings is 1.4975 inches. So your mu is 1.5 clearly, and your x bar is 1.4975. And they want us to test the hypothesis H naught, where mu equals 1.5 inches, versus the alternative hypothesis that mu is different from 1.5 at alpha equals 0.01, or at a 99% level of confidence. And since we are using alternative hypothesis as mu not being equal to 1.5, clearly we are conducting a two-sided hypothesis test. And the part B says what is the p-value for the test. We'll talk about p-value in a second. And part C is compute the power of the test if the true mean diameter is 1.495 inches. So these are the three questions that we want to answer, and we will take these one at a time. So let's begin by answering part A of this problem, where we really start to discuss the 7-step stepwise procedure for hypothesis testing. Okay, so here is the solution that I developed by hand, and we'll go back to Excel and solve the exact problem in Excel, and also explain how it is done in Excel. So let's write the data that we have here. Nominal diameter, which is mu, is 1.5 inches. And it would really help if you guys kind of made notes, or print these notes out. These are on D2L, and kind of followed along. That way these notes make more sense, and this video makes more sense. Sample size n is 25, and sigma is 0.01 inches. All this data is provided to you. The mean of the sample x bar is 1.4975, and we want to test this hypothesis of H naught versus H1 being a two-sided hypothesis. So referring to your 7-step procedure, first, what is the parameter of interest? So that's the first step you want to identify, right? So here clearly the parameter of interest is mu. And stating the null hypothesis, or in our case really restating a null hypothesis, because that has been given to us to test. But if you're working on a project, that is something that you have to determine. Determining the null hypothesis and how to state it, determining the alternative hypothesis and how to state these things. So null hypothesis is H naught mu equals 1.5 inches, and the alternative hypothesis is mu is not equal to 1.5. Once again, there's a two-sided alternative hypothesis, so bear in mind, because we're using a not equal to, it becomes a two-sided alternative. Then let's identify a proper test statistic for this problem. So first one is, since the population is normally distributed and sigma is known, we will clearly use the z statistic. So this is called using the z test. So we'll start to develop what is known as a z naught. We'll call that the test statistic is x bar minus mu divided by sigma over the square root of n. So that is step 4, where we are simply identifying. We won't compute it yet. Computation comes in step number 6. First we want to identify what the appropriate test statistic is for the specific hypothesis. And step 5 is where we state the rejection criteria. And in our case, if z naught is less than negative z alpha over 2, or if z naught is greater than z alpha over 2, which means if either your test statistic lies here or if it lies here, you can reject your null hypothesis. So shaded area is your rejection area, just like we talked about earlier on. But let's kind of take a quick detour and look at what are the three different tests that you can conduct. First thing is what we call a two-tailed test, for which the hypothesis needs to be stated as follows, where h naught is mu equals mu naught and h1 is mu is not equal to mu naught. For an upper tail test or a right hand side test, we are looking at h naught mu equals mu naught and the alternative hypothesis mu is greater than mu naught. For a lower tail test or a left hand test, we are doing h naught is mu equals mu naught and h1 is mu is less than mu naught. And these are, so you're looking at a two-sided test here, an upper tailed test here, and a lower tail test here. So let's take a look at what the rejection criteria looks like. So in this case, the rejection criteria is if the test statistic that you compute, the z naught, if it is either greater than z alpha over 2, which means if it lies in this region, or if z naught is less than negative z alpha over 2, which means it lies in this region, you can reject the h naught. And for the upper tail test, if the test statistic that you computed, which is z naught, if it lies greater or if it is greater than z alpha, or if it lies in this region, then you can reject the h naught in favor of your alternative hypothesis. For a lower tail test, you want if your z naught lies in this region, which means it is lesser than negative z alpha, then you will have the rejection region, or you can reject your null hypothesis in favor of the alternative hypothesis. So please make a note here that since it's a two-tailed, you're trying to do a z alpha over 2 here. Since it's one-tailed in these cases, you're looking at z alpha. This is very similar to your confidence interval analogy. So this is how you look at the rejection criteria. This is called fixed significance level testing, which means you're testing the significance of a hypothesis at a given level. For example, in our case, the bearings problem that we're looking at here, we are being asked to test this at 99% significance or 0.01 alpha level to be able to make a decision of either accepting or rejecting the null hypothesis. So this approach is called a fixed significant level testing. So part B of this problem talks about using a p-value approach to testing, and we'll talk about that in just a few minutes. So let's come back to the problem. So we have a two-tailed test at hand, and step 6 was to compute the test statistic. So z naught, which we want to compute, is the test statistic, is x bar minus mu divided by sigma over square root of n. So we have all these values given to us from the problem. X bar is 1.4975, mu is 1.5. We know that sigma was 0.01, and there are 25 bearing samples that we were looking at. And when you compute this, z naught happens to be, our test statistic happens to be negative 1.25. And we are being given here that alpha equals 0.01, but we want to look at alpha over 2 because it's a two-tailed test. So alpha over 2 is 0.005. So negative z alpha over 2 is z of 0.005, or if you look in your z tables, that value will be negative 2.57, which means the z-score of negative 2.57 gives you a probability of 0.005. Similarly, if you're looking on the right hand side of the table, you need to look for z of 0.995, and that will once again be 2.57. So the z alpha, negative z alpha over 2 is negative 2.57. So at this juncture, pause the video, go back, and or rewind the video to take a look at it again to see if this is making sense. We are computing the test statistic, and we're trying to see where this test statistic lies before you make a decision on the hypothesis. So your rejection region recap, let's kind of quickly recap here. So when do you reject it? You reject your H naught if your Z naught is either less than negative z alpha over 2, or if it is greater than z alpha over 2. But in our case, the negative 1.25 lies between negative 2.57 and positive 2.57. So we fail to reject the H naught. What it really means is we do not have enough evidence to reject H naught. Or so what this really means is that we are failing to reject H naught, and we are not accepting the alternative hypothesis. So what does this practically mean for this bearing example? It simply means that the sample mean and the true mean are not significantly different. They're very close to each other, because our sample mean was 1.4975 and our hypothesized true mean was 1.5, and we wanted to test statistically. So now we can say with some confidence that the sample mean and the true mean are not significantly different, and you can say that with 99% confidence or at a significance level of 0.01. So that is how you solve, you answer hypothesis testing questions using this 7-step procedure. So before we go to part B of the problem, let's understand what p-value really means. So one of the most common ways of representing results of a hypothesis test is by accepting it or rejecting it at a particular level of significance, and that is exactly what we did. So we failed to reject this hypothesis at a level of 0.01. But if you look at it carefully and think about it, there is an inherent problem with this fixed significant level testing. What it is that the computed value of the test statistic that is used does not give a good idea to the decision maker about how far it is in the rejection region or how close it is, right? So is it if you're doing, especially if you're doing one-sided tests, you might not have an idea, a clear idea about how bad or how good it is. So we need to, if to understand that better, what researchers have done, statisticians and mathematicians, is that in the last decade and a half, a relatively new procedure called p-value testing became universally accepted to make and support decisions that you're taking. So p-value is nothing but the smallest level of significance that would lead to the rejection of your hypothesis. So let's read that again. So p-value is the smallest level or the lowest level of significance at which you can reject your null hypothesis. So typically p-value is computed against p-value, whichever is computed, is always tested against a standard value of alpha. For example, if your fixed significance level testing is you're computing that against like 0.01, like we did in the previous example, your p-value has to be lower for you to be able to reject that null hypothesis. So in this bearings case, your p-value has to be greater than 0.005 for us to be able to reject the null hypothesis. So p-value, what it is telling you is the risk of wrongly rejecting the null hypothesis. So lower your risk, the better off we are. So p-value is also called OSL, or the observed significance level. And most uh, software by default compute this value pretty easily. So anytime you run a hypothesis test, most statistical software can give you the p-value, but in Excel I'll teach you how to actually compute this p-value. So once again, let me just try to explain this again, that way this concept is very clear, because it's a very critical concept. So p-value is really the smallest level of significance that would lead to the rejection of the null hypothesis. So a p-value of 0.001 means that the risk of making an incorrect decision regarding the rejection of H naught is extremely small. For example, if your p-value was zero point 0.3, there is a 30% chance of you making an incorrect decision while rejecting the H naught. So smaller the p-value, the stronger evidence you have to reject the null hypothesis. So now let's figure out how to apply these principles and solve the hypothesis testing problem. So technically you should arrive at the same decision using both fixed significance level testing and the p-value testing. So let's look at this diagram here for p-values. For a two-tailed test, you have these two regions here for an upper tail test and for a lower tail test. So the way you compute it is, if you have a test statistic, you can actually use that test statistic to compute the p-value. So it is simply 2 times 1 minus phi of the absolute value of your test statistic, because you're looking at both regions. So you're essentially computing p-value is simply computing this area. So this area beyond the test statistic on both sides. Similarly, if you're doing an upper tail test, you're looking at this area. The way you compute it is 1 minus phi of z naught, because phi of z naught is going to give you this area. So 1 minus phi of z naught is going to give you this particular area. But if it's a lower tail test, I can compute the p-value pretty easily. All you need to do is directly phi of z naught, because you're trying to find this particular area. So, and once again, z naught is your test statistic, so don't forget that. And sometimes, like in the previous example, the one we tried before, the foam height and the shampoo example, remember we had already an acceptance region that was given to us. So if an acceptance region has been given to us, you can compute the p-value as follows. So all it is one, for example, let's say, sticking with this problem, your mu is 1.5, and let's say the acceptance region, I'm just throwing this example, these values do not pertain to this problem. So if my acceptance region is between 1.4 and 1.6, if I want to find the p-value given these values, given these critical values, I can compute that as 1 minus the probability that x bar lies between 1.4 and 1.6. Okay, this is when the acceptance, not accepted, but acceptance region is given to us. But in typically the acceptance region is not given to us. We have to determine that based on the level of significance at which you're testing. So the test statistic will give you that information. Sometimes you may have the acceptance region. Maybe you might know that you want to accept this hypothesis, if it, or accept this the acceptable value maybe between a couple of in a particular range. If that value is given, you use this approach. Otherwise, we can use this approach. Alright, so what we'll do is, let's figure out how to compute this. So coming back to the question at hand, so we're looking at a two-tailed test. So we know that p-value is nothing but 2 times 1 minus phi of z naught. Phi is simply, a notation for telling you the phi is the z value of negative 1.25. That's what that is. We know that z naught that we computed before is negative 1.25, but that negative 1.25 is within, it's an absolute value, because we're looking at a two-tailed test. So 2 times 1 minus phi of the absolute value of negative 1.25, or in other words, simply phi of 1.25, or the z value of 1.25. And that is, or the probability is 0.8943. And when you simplify, you will end up with 0.2114. Clearly, this p-value is not less than 0.01. So we know that there is high risk, a very high risk of making a wrong decision by rejecting the H naught. So in this case, we fail to reject the H naught. Clearly, the p-value approach here and the fixed significance level testing have yielded, and they need to yield, the same conclusion. We need to arrive at the same conclusion. And I want you to try part C for yourself, which is really identifying or calculating the power of the test, and your answer, just to check, the power of the test must be 0.47. And if you have any questions, you can send me an email, and I can try to explain it, or give me a call during my office hours and we can talk. But it should be pretty straightforward. You can compute the beta, and the beta at I believe 1.495 is being given as a true mean, so you can compute that value, and we already solved a couple of examples earlier on. So what we'll do next is we'll take this exact example, the same example, and solve it using Excel, and then there's a data set that is posted on D2L, and we'll solve another practical example, a little bit larger example, once again using Excel to conduct a hypothesis test.